Chapter 2, the atmosphere. So the atmosphere is the medium in which an aircraft operates, and it is the properties of the atmosphere changed by the shape of the wing that generate the required lift force. The most important property is air density, so thickness. Let's think of this as mass flow over the wings in terms of kilograms per second. A given mass flow will generate the required lift force, but a decrease in air density will reduce the mass flow. So to maintain the required lift force, if density is decreased, the speed of the aircraft through the air must be increased. So the increased speed of airflow over the wing will restore the mass flow and lift force to its previous value, as it says here. So let's say, for example, 1 kilogram of air per second is passing over and under the wings. If the mass decreases, so the density decreases, let's say instead of 1 kilogram, 0.5 kilograms. 0.5 kilograms would need to pass over the wings not in 1 second but in half seconds, so that in 1 second there will be a total of again 1 kilogram, if it makes sense. So there is the same amount in 1 second of a kilogram that passes through the wing, so because it needs to be faster. So 0.5 kilograms in half second would be 1 kilogram per second. So physical properties of air. Air as substance. A mass of moving air has considerable kinetic energy. For example, when moving at 100 knots, the kinetic energy of air can inflict severe damage to man-made structures. Air is a compressible fluid and is able to flow or change its shape when subject to even minute pressure differences. The viscosity of air is so low that very small forces are able to move the molecules in relation to each other. When considering the portion of atmosphere in which most aircraft operate, so up to flight level 400, with increasing altitude, the characteristics of air undergo a gradual transition from those at sea level. Since air is compressible, the lower layers contain much greater part of the whole mass of the atmosphere, if it makes sense. So air is compressible, so the lower layers close to sea level is where it contains much greater of the whole mass of the atmosphere, because the weights of the air plus the gravity will make so it compresses. So at sea level there is much more air than as much as you climb, there will be much less air. So pressure falls steadily with increasing altitude, but temperature falls steadily only to about 36,000 feet, where it then remains constant through the stratosphere. So static pressure. The unit for static pressure is newtons per squared meter, and the symbol is lowercase p. So static pressure is the result of the weight of the atmosphere pressing down on the air beneath, as I was saying before. Static pressure will also exert the same force per square meter on all surfaces of an airplane. The lower the altitude, the greater the force per square meter. It is called static pressure because of the air's stationary or static presence, because it's not moving. Also, an aircraft always has static pressure acting upon it, like all objects, like everything. Newtons per square meter is the standard international unit for pressure. 1 Newton per square meter is called a Pascal, and it's quite a small unit. So in aviation, the hectopascal is used. Hecto means 100, so 1 hectopascal is the same as 1 millibar. Static pressure at a particular altitude will vary from day to day and is about 1000 hectopascals at sea level. Or in some countries, such as in the US, is measured in inches of mercury, as you can see here. Sea level static pressure is about 30 inches of mercury. Now we'll talk about temperature. The unit of temperature is degrees Celsius or centigrade, and when this is measuring, of course, to the freezing point of water, or Kelvin when measured to the relative absolute zero. So 0 degrees Celsius is equivalent to 273 Kelvin. Temperature decreases with increasing altitude up to about 36,000 feet, and then remains constant, as we were saying before. Now, air density, very important. The unit for air density is kilogram per cubic meter, and the symbol is the Greek letter rho. Density is mass per unit volume, so the number of air particles in a given space, as you can see here of its unit. So how many particles of air, what's the mass of this air in a given space, which will be a cubic meter. Density varies with static pressure, temperature and humidity. So density decreases if static pressure decreases. So the higher you go, the less static pressure there is, so the less density there is. Density also decreases if temperature increases. So in a very hot day, let's say 40 degrees Celsius, density is lower than colder day at 10 degrees Celsius. Density decreases if humidity increases. We'll talk about this later. Water vapor is less dense than a dry air. In a few words, air density is proportional to pressure and inversely proportional to temperature. This means that air density increases with an increase in static pressure, but air density decreases with an increase in temperature, as we were saying before. So we can say that in a few words that it's true that density decreases with increasing altitude because of decreasing static pressure. However, with increasing altitude, temperature also decreases, so density should get again high. But the effect of decreasing static pressure is dominant, which means that the effect of static pressure, so decreasing with altitude, so the static pressure will decrease air density, has a stronger effect than the fact that with increasing altitude the temperature decreases. So with a decrease in temperature should give you a higher density, but the effect of static pressure is dominant over temperature. We can talk now about International Standard Atmosphere, ISA. The values of temperature, pressure, and density are never constant in any given layer of the atmosphere. To enable accurate comparison of aircraft performance and the calibration of pressure instruments, a standard atmosphere has been adopted. So Europe uses the standard atmosphere defined by the International Civil Aviation Organization, ICAO. An ICAO standard atmosphere assumes the following mean sea level values. So these values are mean sea level. So a temperature of 15 degrees Celsius, a pressure of 1013.25 hectopascal, and a density of 1.225 kilograms over cubic meter. The temperature lapse rate is assumed to be uniform at a rate of 2 degrees Celsius per 1000 feet. More precisely, 1.98 degrees Celsius from mean sea level up to a height of 36,090 feet, above which the lapse rate becomes 0 and the temperature remains constant at minus 56.5 degrees Celsius. So the lapse rate is a standard lapse rate of 1.98 degrees per 1000 feet. Of course, this changes depending on the day, and it can be different. Can be 3 degrees per 1000 feet. Can be then again reaching 2000 feet. Can be 1 degree, but the standard is 2 degrees per 1.98 degrees Celsius per 1000 feet. We can see here that at 40,000 feet, air density is about 1/4 of the one at sea level, and at 20,000 feet is about half. Now we'll talk about dynamic pressure. The unit for dynamic pressure is Newton per square meter, and the symbol is lowercase q or uppercase Q. So this is dynamic pressure. This is the pressure caused by the air moving towards an object. Because air has mass, air in motion must possess kinetic energy and will exert a force per square meter on any object in its path. As we remember, kinetic energy equals half of the mass multiplied by square speed in meters per second and mass in kilograms. It is called dynamic pressure because, as I was saying before, the air is moving in relation to the object being considered, in this case an aircraft. Dynamic pressure is proportional to the density of the air and the square of the speed of the air flowing over the aircraft. So an aircraft immersed in moving airflow will therefore experience both static and dynamic pressure. So static is always there, and dynamic pressure whenever air is moving relative to the object. The kinetic energy of 1 cubic meter of air moving at a stated speed is given by the formula kinetic energy equals half rho multiply square of speed, and it gives you result in joules, where rho, as we said before, is the local air density in kilograms per cubic meter, and v is the speed in meters per second, as always. So again, from this formula, we just applied half of the mass. The mass of the air, we said, is measured in kilograms per cubic meter. So we use this formula. Half of the mass, which means half of the air density in kilograms per cubic meter, multiplied by the square of speeds in meters per second. If this cubic meter of moving air is completely trapped and brought to rest by means of an open tube, the total energy will remain constant, but being brought completely to rest, the kinetic energy will become pressure energy, which for all practical purpose is equal to half rho multiplied by square speed, and will give you newtons per square meters, because this again, this energy becomes a force, and force is measured in newtons per square meter. So let's consider air flowing at 52 meters per second, which is 100 knots. So let's remember to find meters per second are about half nautical miles per hour, or knots. So 100 knots, approximately 50 meters per second, 2 meters per second, approximately 4 knots. So consider this air flowing at 100 knots with a density of 1.225 kilograms per cubic meter. So let's first see how to convert these 100 knots. So 100 knots multiplied by 6,080 feet, because 6,080 feet equals to 1 nautical mile. 1 knot is saying the same as 1 nautical mile. So 100 knots we multiply, and it will give us feet. It's giving us 608,000 feet per hour. Now let's say we want to convert this into meters. So we know that 1 meter equals 3.28 feet, or 3.28 feet equals 1 meter. So if we divide this 608,000 feet divided by 3.28, it will give us 185,366 meters per hour. Now divided by 6 we have minutes, divided by 60 we have minutes, divided by 60 we have seconds, and so this gives us 52 meters per second. Now we can work out the speed. So let's apply the formula. Dynamic pressure of this density at this speed is, let's halve this density as it says here. We have to halve it, so we multiply by 0.5, multiply square of speed, multiply 52, and it gives us 1,656 newtons per square meters, which will be 16.56 hectopascal. As we can see here, if speed is doubled, dynamic pressure will be 4 times greater. As we can see here, speed is doubled, and this is 4 times greater. If the area of the tube is 1 square meter, a force of half rho square speed newtons will be generated. Force equal pressure multiplied by area. So we can say dynamic pressure half rho multiply square speed is common to all aerodynamic forces and determines the air loads imposed on an airplane moving through the air. So the symbol for dynamic pressure, Q, letter Q, we can say that Q is equal to half rho multiply square of speed. Key facts. A pilot needs to know how much dynamic pressure is available, but dynamic pressure cannot be measured on its own because static pressure will always be present. So the sum of static pressure, the static and dynamic pressure, is known as total pressure, or stagnation or pitot pressure. So total pressure equals static pressure plus dynamic pressure, because you need to consider both of those. There is dynamic pressure on a certain body, but the static pressure is always present, so you need to add that as well. This can be arranged so that the total pressure minus static pressure will give you dynamic pressure. So if you know the total pressure, if you have an instrument to measure total pressure, and you know static pressure because you know the air density, you know the altitude at which you're at, you can calculate your dynamic pressure, so the flow of mass of air over your aircraft. This is very important. Because dynamic pressure is dependent upon air density and the speed of aircraft through the air, it is necessary for students to fully appreciate the factors which affect air density. Again, let's recap. Temperature, increasing temperature decreases air density. Static pressure, decreasing static pressure decreases air density. Humidity, increasing humidity decreases air density. The reason, we can talk about it now, increasing humidity decreases air density is that the density of water vapor is about 1/8 that of dry air. Increasing altitude will decrease air density because the effect of decreasing static pressure is more dominant than decreasing temperature. So dynamic pressure is so important that we need to have an instrument, a mean for measuring dynamic pressure. A sealed tube open at the forward end is located where it will collect air when the aircraft is moving. The pressure in the tube, the pitot tube, in fact, is dynamic plus static, and in this context it's called pitot pressure because the air is inside the pitot tube. As we were saying before, pitot pressure is the same as saying static plus dynamic pressure or total pressure. So there must be a way of removing the static pressure from the pitot pressure. The way this is done is by a hole or vent in a surface parallel to the airflow will send only static pressures, which is parallel. As we can see here, this is a static vent. Airflow will be parallel, so there will be no airflow going into this hole. Referring to the diagram below, if the pressure from the pitot tube is fed to one side of a diaphragm mounted in a sealed case, and static pressure is fed to the other side, the two static pressures will cancel each other, and the diaphragm movement will be influenced only by changes in dynamic pressure. So, which means that the static vent will apply a little bit of pressure on the other side of this diaphragm, just enough to cancel the its parts of the total pressure, so the static pressure. So the static pressure will exert an opposite force to the needle, just as much as as much static pressure there is. So in a way that when the total pressure will be fed to the instrument, only the dynamic pressure will be indicated in the instrument because of the static pressure acting on an opposite way. So movement of the diaphragm moves a pointer over a scale, so that changes in dynamic pressure can be observed by the flight crew. By the instrument, but the instrument is calibrated at ISA sea level density. So the instrument will only give a true indication of the speed of the aircraft through the air when air density is 1.225 kilograms per square meter, which is, as we know, is not always the case. This is not a problem because the pitot needs an indication of dynamic pressure, because this is important to generate lift, and this is what the instrument provides. The instrument is made in such a way that indicates the square root of the dynamic pressure in nautical miles per hour, or statute miles per hour. So if this indicated speed is doubled, the speed of the aircraft through the air will also be doubled. So let's talk about speeds a little bit. So the first speeds we have, the basic form is indicated airspeeds. The speed register on the airspeed indicator, ASI. Then we have calibrated airspeed, an accurate measure of dynamic pressure when the aircraft is flying slowly, the position of the pitot tube and static vent or vent, together with the aircraft's configuration, flap, landing gear, etc. And attitude to the airflow, angle of attack and side slip will affect the pressure sensed, particularly the pressure sensed at the static vents. So when the airplane is flying level, straight, at a certain speed, that's the way it is being calibrated. It reads a certain speed. But if the airplane is flying, for example, side slip, and for example there's more air getting into the static vent, which will be at the side of the airplane, or the pitot tube is angled, like for example upwards. If the angle of attack is very high, the pitot tube will be angled upwards and will be less air flowing to the pitot tube. So there is a way to calibrate the speed to account for this error. So under the influence of the above conditions, a false dynamic pressure, IAS, will be displayed. When IAS is corrected for this position or pressure error, it's called calibrated airspeed. After that, we have, after a indicated airspeed has been corrected for any instrument, any pressure or position error, it becomes calibrated airspeed. Now we have equivalent airspeeds, an accurate measure of dynamic pressure when the aircraft is flying fast, entering the pitot tube. So the air entering the pitot tube is compressed, which gives false dynamic pressure IAS reading. This only becomes significant at higher speeds. So the air gets compressed and it gives false indication. So at any given air density, the amount of compression depends on the speed of the aircraft through the air. So when IAS is corrected for position and compressibility, the resultant is EAS, equivalent airspeed. So CAS corrected for compressibility gives EAS, or equivalent airspeed. After this, there is true airspeed, or V. That's the final speed. The speed of the aircraft through the air, basically. The only speed there is, as the book says. All the other so-called speeds are pressures. So this is the actual speed of the aircraft through the air. The airspeed indicator is calibrated for standard sea level density. So it will only read true airspeed if the density of the air through which the aircraft is flying is again the standard density, 1.225 kilograms per square meter. Thus, at 40,000 feet, where the standard density is 1/4 of the sea level value, to maintain the same EAS, the aircraft will have to move through the air twice as fast. The speed of sound, A. Sound is weak pressure waves that propagate spherically through the atmosphere from their source. The speed at which pressure waves propagate is proportional to the square root of the absolute temperature of the air. The lower the temperature, the lower the speed of propagation. So in a colder air, speed can propagate at a faster rate. On a standard day at sea level, the speed of sound is approximately 340 meters per second, about 660 knots true airspeed. At higher aircraft true airspeeds and or higher altitudes, it is essential to know the speed of the aircraft in relation to the local speed of sound. The speed relationship is known as the Mach number. So, at higher altitudes, with a decreased temperature, for example, we said minus 56 degrees Celsius, the sound propagates at a faster speed. So we need to know the relation of the aircraft to the Mach number, because if the speed of sound at sea level on a standard day is 660 knots, at 40,000 feet it could be much lower, and the airplane could be flying very close to the speed of sound. So Mach number is true airspeed over A, which is local speed of sound. So if the true airspeed of the aircraft is 4/10 the speed at which pressure waves propagate through the air mass, the Mach number will register 0.4 Mach. Critical Mach number. The critical Mach number is the Mach number of the aircraft when the speed of the airflow over some part of the aircraft, usually the point of maximum thickness of the airfoil, first reaches the speed of sound. So the point of maximum thickness of an airfoil, as we will see later, is the point where air accelerates. So the critical Mach number is that point when the speed over the speed of the airflow over this part of the wing, where air accelerated reaches the speed of sound. So that's the first part of the airplane that reaches the speed of sound, while the rest of the airplane is at a little bit lower than the speed of sound. So airspeed. The airspeed indicator is really a pressure gauge. The needle of which responds to changes in dynamic pressure. Half rho multiplies square speed. This is very important. The airspeed indicator is a pressure gauge. Calibration of the airspeed indicator is based on a standard sea level density, 1.225 kilograms per square meter. The airspeed recorded will be different from the actual speed of the aircraft through the air unless operating under standard sea level condition. Unlikely, it says here. The actual speed of the aircraft relative to the free stream is called true airspeed and denoted by the letter V. The speed recorded by the airspeed indicator, calibrated as above, if there are no other errors, is called equivalent airspeed. Okay, errors and correction. An airspeed indicator is, however, also subject to errors. Other than that, due to the difference between the density of the air through which it is flying and a standard sea level density. So there is instrument error. This error may arise from the imperfections in the design and manufacture of the instrument and varies from instrument to another. Nowadays this is very small and can be disregarded. When any instrument error does exist, it is incorporated in the calibrated airspeed correction chart for the particular airplane. So they will calculate any errors or instrument errors. So whenever you have your calibrated airspeed, some manual will give you a planned or calculated even true airspeed, which is correct, calibrated airspeed corrected for temperature. So everything is instrument errors taken into account on the manual of the aircraft. Then there's position error, pressure error. This error is of two kinds, one relating to the static pressure measurement, the other to the pitot pressure measurement. As I was saying before, the pitot tube and static ports may be mounted in a position on the aircraft where the flow is affected by the presence of the aircraft. Changes in configuration and proximity to the ground, everything can affect the airflow passing through these two vents, the hole in the pitot tube and the static port. So if so, the static pressure recorded would be the local and not the free stream values. The pitot pressure may be under-recorded because of incorrect alignment with the air free stream. The tubes may be inclined to the airstream instead of facing directly into it. So changes angle of attack, as I was saying before. So the magnitude of the consequent errors will generally depend on the angle of attack. Compressibility error at high speeds. The dynamic pressure is not simply half rho multiply square speed, but exceeds it by a factor determined by the Mach number. Thus, the airspeed indicator will overread. So it will overread when air is being compressed. Depending on the Mach number, will be compressed and will give you a higher reading than what's actually is. So this is very important. V speeds, for example, VS, V1, VR, V2, VMD, VMC, VYC, many others. These are calibrated airspeeds because they relate to aircraft operations at low speeds. However, the appropriate corrections are made and these speeds are supplied to the pilot in the flight manual as indicated airspeeds. So BMO, the maximum operating indicated airspeed is, however, an EAS because it is a high speed, but again is supplied to the pilots in the flight manual as an IAS. So the speeds are calculated and calibrated as EAS, CAS, calibrated airspeed, but the pilot reads only his airspeed indicator. So it needs to be corrected again backwards to match what the pilot will read. So if the calibrated airspeed will be 60 knots, but the pilot in reality reads a little less, 55. The VMO read by the pilot will be 55 in indicated airspeed, although what's being calculated was 60 in reality. So to sum up, dynamic pressure Q is affected by changes in air density. So Q equals half rho. Rho is the air density. Standard is 1.225 kilograms per square meter, and this multiplied by square of speed. Air density decreases if atmospheric pressure decreases. Air density decreases as well if temperature increases, and air density decreases if humidity increases. With the aircraft on the ground, taking off from an airfield with low atmospheric pressure and high temperature and high humidity, this will require a higher true airspeed to achieve the same dynamic pressure. As we said here, if all of this, if the air density is decreased by a lot, let's say here, low atmospheric pressure, high temperature and high humidity, speed must be increased to obtain the same lift force, and the same as saying here, to achieve the same dynamic pressure, indicated airspeed. So for purpose of a general understanding, a constant indicated airspeed will give constant dynamic pressure. Increasing altitude decreases air density because of decreasing static pressure. With the aircraft airborne, as altitude increases, a higher true airspeed is required to maintain a constant dynamic pressure, because of course density decreases. Maintaining a constant indicated airspeed will compensate for changes in air density. So, constant indicated airspeeds means that the airspeed indicator is reading a constant dynamic pressure, which means that you're actually going faster, because if the dynamic pressure is indicated to be the same, for example 80 knots, but you know that air density is decreasing, so dynamic pressure should be decreasing unless speed is increasing. So climbing at 80 knots indicated airspeeds will give you it will compensate for the decreasing in air density, because the instrument reads what actually is passing over the wings. There is only one speed, the speed of the aircraft through the air, the true airspeed. All the others, so-called speeds, are pressures. The airspeed indicator is a pressure gauge. Aircraft V speeds are calibrated airspeeds, except BMO, which is the maximum operating speed, which is an EAS, equivalent airspeed. but all are presented to the pilot in the flight manual as indicated airspeeds, because this is the only thing that the pilot will read on his airspeed indicator.